Hello, this lab is about the file system details in the Pintos. Block device refers to the storage, like SSD or hard disk drive, and such and so forth. And block device consists of a block. It's a set of blocks. It's a linear array of blocks, and each block has its number. We call it a logical block address, LBA. In some context, each block refers to the 512-byte sector, or in some context, it refers to the 4 kilobyte file system block. So you have to check whether what LBA refers to in each occasion. This is how we represent a block device in Pintos operating system. This is data structure. The name of the data structure is block. And the most important attributes for the block is the size, probably the size of this in terms of sectors. And then Pintos allocates a 16 character length name as an attribute for the block device. Then there is a block device type, and then there's pointer to the device driver, which contains a set of operations defined for the specific block device. And then Pintos defines a read count and write count for a block device, which refers to the number of sectors read and sectors written. So this is the block device. And then formatting a file system is process of writing some contents over each of these blocks. This is the layout of the Pintos file system. This is this is block. So block 0, block 1, block 2, block 3, and block 4, and such and so forth. And here in Pintos, each block is 512 byte. So the file system block size is determined by the file system. You can format a file system with 4 kilobyte block, or you can format a file system with 32 kilobyte block, or even you can format a file system with 5 terabyte block. Here in Pintos, they use 512 byte as a sector size as well as file system block size. This is a basic sample layout of the file system in Pintos. The first block, there is an inode for the bitmap. So bitmap is a data structure which determines whether each of the block is being used or not. And second block is occupied by the inode for the root directory. And then there comes a 4 block. It represents a bitmap for this file system partition. And there's the root directory. Of course, I'm going to explain each of these data structures in detail as we go on. And there is, and so here, creating the inode for the bitmap, and creating the inode for the root directory, and creating and initializing the bit stream, and creating the root directory, this part, and initializing and saving the initial value of this data structure is called formatting of file system. So basically, formatting a file system is from the clean block device, you write initial values for the essential data structure that is required to operate the file system. Let's look at the bitmap size. Here, we allocate 4 sectors, 4 blocks, but each block corresponds to a sector, and each sector is 512 bytes. So we are allocating 2048 bytes for a bitmap, and it corresponds to 16,384 bits. Okay, so in bitmap there are 16,384 bits, and each bit represents whether a given sector is free or being used. So if we multiply the number of bits in the bitmap by the sector size, then we're going to get the file system size. So Pintos, in this file system partition, you have 8 megabyte. So if you have 4 sectors for bitmap, then that can cover 8 megabyte file system partition. So if you double the bitmap to 8, then of course it's going to cover 16 megabytes file system partition. So this is how it works. Then from now on, I am going to explain how each of these fields are occupied and initialized at the file system boot stage. So formatting a file system in Pintos creates basically 3 steps. First one, create and initialize how each of these sectors in the file system partition is being used. Of course, most of the sectors are free at the file system partition phase. And then after creating a bitmap, you regard a bitmap as a file. So bitmap is also a file. So you create an inode for a bitmap also. And the basic data structure for the file system is the root directory. So you have to also create a root directory. Of course, after you creating an inode for a bitmap, you have to write it to the disk. Write the bitmap to the disk to synchronize the file system states to the disk safely. Okay, there are 3 steps. Create and initialize the bitmap. This is first step. And the second step, create inode bitmap and write its data on the disk. This is second step. The third step is create inode of a root directory. This is third step. Step 1, step 2, and step 3. Okay. So in the course of formatting a file system, you write from sector 0 or from block 0. I'm using the sector and block interchangeably, especially in the Pintos file system, because in Pintos file system, each block corresponds to a sector. So so formatting a file system in Pintos corresponds to writing and initializing the first 6 blocks in the file system. So inode block for a bitmap, inode block for root directory, and initializing inode bitmap. And this part is tricky. At the beginning, when the file system is first created, the empty directory for the root directory is created, but it's not going to have any contents inside its directory. Let's see how it happens. Okay. So this is the code for initializing the file system. It is in the function filesys.c. The name of the function is filesys_init. Okay, so it contains 3 basic steps: initializing the inode, and initializing the bitmap, and perform format. Okay, so what does it correspond to? We're going to look at the details. First, the function inode init is create and initializing the data structure for open files. Okay, when the system is first created, the file system first boots up. There is two basic word in computer system. First one is memory. The second one is disk. So when the system starts, which we call a system boots, you create an empty list that is a list of open files, and inode is the data structure that represent a file. And also in a free map init, you have to create a bitmap that can cover 8 megabytes, and you have to initialize it properly. And formatting, the formatting is writing this data structure to the disk properly. Okay, this is, and also the formatting here has two things. First one is the create and write the bitmap file. And the second part of the formatting is create the root directory. That's two important things. So remember, initialize the inode, like this, initialize the bitmap, and then perform format. Format is the process of writing the bitmap to the disk, and the process of creating the root directory on the disk. And creating the file consists of two parts. First one, creating the inode, and second one, creating the data blocks associated inode. So create the, okay, let's move on. So this is the process of initializing the file system. We call it a format. Okay. So as we saw before, the first two important part is create the empty inode list for open files. Second thing is create the bitmap, and then perform format. Format consists of creating. Okay. Creating the inode of bitmap file and save it to the disk for to save the disk from the crash recovery, and then create the root directory. There are two things. Okay, let's look at the actual code. So first thing we have to do is initialize a list of open inodes. It corresponds to initializing the list of in-memory inodes. So inode init function, it calls list underbar init. This is a typical function that initializes the empty inode list at the beginning, and it has open inodes. So this is the essential function to create the list, empty list. Okay. So this in Pintos, as you see, it maintains a set of inodes for the opener files as a linked list. My question is, what is the data structure that represent open files in x86 operating system? Probably the Pintos and x86 are most widely used operating system for operating system education. They are using slightly different data structure for representing each of the concepts in the operating system. So we in the class, in the textbook, we are using x86 code, and in the lab we are dealing with the Pintos 6. So if you are interested in different ways of implementing the operating system concept, you may want to read both of the codes for comparison purpose. So my question is, what is the data structure that represents the open files in x86? Please check it out. So the first step is creating and initializing the bitmap. So first, you create the bitmap of block size. So here, the file system is 8 megabytes, as we saw before. And then at the very beginning, we need two inode. One inode for bitmap, and the other inode for root directory. So we have to mark those bitmap as being used. And we're going to allocate inode for the bitmap at sector 0. And we're going to allocate the inode for the root directory at sector 1. So you have to mark the associated bitmap, associated entry in the bitmap. So this is location we're going to mark. This is location we're going to mark also for root directory. And this is the pointer to the array of bitmaps. Okay. So the next, in the initial line of file system, there are 3 steps: creating the inode of bitmap, and of course after you are done with initializing the bitmap array, you have to write them to the disk for synchronization purpose. And then you have to create the root directory. Writing the contents of the bitmap to the disk and create the inode of the root directory to the disk. Okay, so in this function, there are two steps. Create the free map file, and then second one, create the root directory. So there are two things you have to do. First one, creating the bitmap file, and second one, creating the root directory. And especially the root directory, the second parameter is number of entries in the directory, And here, you are initializing the root directory with maximum of 16 entries. And this is the location of the inode where you are going to place the inode for the root directory. The first one, the first step, create and save the bitmap file. So you create the inode and write it to the disk. This is actual code for creating a bitmap. So you have to first create the inode for the bitmap. This is the first parameter, is the location of the inode where you want to create the inode for a given file. Okay, there are two functions you want to pay attention to: inode create and file open and bitmap write. So after creating the inode for a bitmap file, you bring those inode to the memory and save the contents of the bitmap to the disk. So these are three basic functions for creating a free map. Next thing is creating a root directory. Creating a root directory corresponds to creating an inode for the root directory. So creating an inode at this location of inode, and then the size of the directory entries. So again, the inode create accepts two parameters. First one is sector. This is block number, which is the inode for the root directory. And entry count is the maximum number of entries in the root directory. So you specified it as 16 in the code. And the second thing is, after you creating an inode, of course, every directory need a place to save the directory entry other than the inode. So you have to allocate the data blocks for the root directory, and you have to save the start address of the data block at the inode. So there is two functions. Bytes to sector is a simple function that translates the number of bytes into the number of sectors. And then the free map allocate is allocate a certain amount of data blocks from the bitmap. And so allocate contiguous blocks. So for example, you want to allocate, for example, 16 sectors. Then what you have to do is you have to scan the free bitmap and looking for the consecutive bits array where all these bits arrays are free. So this is 16 bits are free, for example. You find that this block is, this bit is occupied, it's not occupied, it's occupied. Of course, this bit is occupied, but because the next bit is being used, even though this 0, 1, 0, 1, 2, 3, even though the third bit is free, because the fourth bit is being used, you cannot allocate consecutive 16 bits. So if you find consecutive 16 bits are free, then you allocate consecutive 16 bits and corresponding blocks, and then returns the start address of the corresponding sectors. That's what free map allocate is used. And then you have to save the starting address at the associated inode at the starting point. Okay. Then you write disk inode to the disk safely. Because one thing you have to make sure is memory, we call it as a DRAM, is volatile. Volatile means that if the powers go off, then you lose all the contents. Storage, which usually is a disk, is non-volatile. If you save the contents of the disk, you can have it even though the power goes out. So, but every operating system operation deals with memory data structure. So you have to be careful, and if the data structure needs to be saved carefully and saved safely, even with the existence of power crash, then you have to make sure that every data structure needs to be stored at the disk safely when the operation completes. So this, you write the disk inode to the disk. Okay, and then after you're writing the bitmap contents to the disk, then you close the inode. And then after closing the inode, you deallocate and remove the in-memory inodes from the open inode list and save it to the disk. The next step to do is to load the bitmap to memory. So it's read the bitmap contents on the disk from the disk to memory. So it consists of two phases. First one is open the file and then read it. Now we're going to explain the details of creating a file. Creating a file is done by creating the file system. Filesystem4-background. Filesystem4-background. This is the driver function of the system called create. So by looking at these details of the code, you're going to learn how the file system create a file. So creating a file consists of creating the inode. Let's think about what kind of data structure we have to modify in creating a file in the file system. Okay. Let's say we are going to create a file. Then we have to create the inode for a new file. And then of course you may want to initialize the data blocks associated with the given file. Okay. And then you have to modify the directory, parent directory which the newly created file belongs to. For example, let's say the name of the file is a.c. And then a.c contains a pair, which is file name and inode number. Okay. So this is data. So this is the new file, data block, and the associated inode. And then there is a directory block. Is that all? Actually, there is one more thing. So there is a bitmap, the file system. So we have 4 sectors. We have allocated 4 sectors in the file system. Let's say first sector, second sector, and third sector. And because you have allocated 2 blocks, one sector for inode and one sector for data block in this specific example. So you may have updated some part of this bitmap. Let's say you have updated 2 bits in the third part. Okay. Then in the course of creating a file, you have updated at least 4 blocks. The first block, and second block, and third block, and fourth block. 1, 2, 3, and 4. So in the course of creating a file, we have updated and modified 4 blocks. We have to synchronize all these blocks to the disk. So as you can see, creating a file is non-trivial exercise. So the details of the file system is create and initialize an inode, write it to the disk, and then add new entry in the root directory. Okay, this is the simplified steps of creating a file. In this example, they did not allocate any data blocks, and it does not show how the bitmap is allocated and updated, but we are going to show how it works. So this is detailed steps of creating a file. The name of the file is test file. So we call a function file system create test file. Okay, so very first step is to read the inode of the root directory from the disk to memory and insert it to the open inode list. The second step is write the inode of the test file to the disk, the create inode, and then read the entries on the root directory, and then add a new directory entry for the test file, and then write the entries of the root directory. Okay, so it consists of 5 steps. Then let me ask you a question. Among these 5 steps, it only shows the steps of modifying and updating the inode block and directory block. Inode block and directory block. Directory block is updated, but inode block is newly allocated. So in the course of allocating a new block for inode, we have to update bitmap. We have to mark the associated, we have to find the free block and mark the associated bitmap as marked. Okay. Then which of the 5 steps, 3, 4, 5, we have to include, where do we have to include, or where do we have to insert the process of updating the bitmap? Let's say this is 1.5, 2.5, 3.5, 4.5, and 5.5, and 0.5. Where among these possible 6 positions, where do we have to include the process of finding the free entry in the bitmap? Where? Think about it. Of course, the answer is going to go up. Answer is going to show up shortly. Okay, let's move on to the next page. The file system create consists of, well, there comes an answer right after. We first have to open the root directory. And then the file system, the creating a file consists of creating an initialized inode and add new directory entry to the root directory. In the current Pintos file system here, we do not have hierarchical directory structure. We only have root directory. So open root directory. And if the root directory is successfully opened, okay, then we allocate free block. And this is number of sectors you want to allocate. This is number of sectors. Number of sectors you want to allocate. And then in the course of allocating a new block, you insert the start address of those sectors in the specified inode address. Okay, so FreeMap allocate here specifically, it allocates one sector as specified here from the FreeMap, and then save the start address at the inode sector. This is how you create the sector. So in the course of calling free map allocate inside of this function, it automatically updates the free bitmap array. And then it calls inode create. In the course of creating an inode, it initializes an inode with initial size byte and write it on the disk. And then add the created directory entry to dir specified as a parent directory of the just created file. Okay. So this is how we creating a file. Now, let me explain the procedure of opening an inode for the first time. So the function in concern is inode open. It read on disk inode at sector. So this is first parameter. So it reads the inode from the disk at the sector location and then create its pointer. Of course, the important operation of inode open is inserting the read inode to the linked list of the open inode here. So Pintos maintains a list of inode, list of open inode in the system. It is global linked list. And in the course of opening an inode, you have to insert these inode to the list. So this is the process of inserting an inode to the open inode list. Okay. And then you have to set the field properly. Okay, there is one important field you may want to pay attention to. There's this open count. This is open count. More than one process can open a file, and then if there are two processes, process 1 and process 2, and both of the file calls a function open f.c, for example. Then the same file is opened twice by different process. In this case, this open count is set to 2. So this represents the number of processes that opened a given file. Opening a directory is similar to opening a file, except that directory entries are opened instead of the inode itself. So directory open function gets the inode pointer as its parameter. And in opening a file, it allocates directory structure and read the disk entry, read the directory entry, and initialize the field of the directory structure with the inode and the associated position. Then the important function, most essential function, is allocating a free block. This is function free map allocate. So it accepts two parameters. Two parameters. First one is count. The objective of free map allocate is find CNT consecutive free blocks, scanning free block. So CNT stands for the number of blocks to allocate. And as a result, the sect or sector position, sector P, specify the start address of the blocks allocated. And then in the course of allocating a free block, it sets the free bitmap. So my question at the beginning of this few slides back, was where the free block bitmap is updated in the course of allocating a new block. It is within free map allocate. So find the consecutive first bitmap, or false bitmap is a bitmap is setting with 0, and set them to true. The next function is how we create a directory. A few slides before, we look at the function that create a file. Now we are looking at the function of how we create a directory. Okay, so it has, what we would like to do is add a name file to the directory. And inode of the file that needs to be inserted is at inode sector parameter. So it has three parameter: name, directory, and inode sector. Okay, so directory is a target directory where the newly created file is located, and the name of the newly created file, then associated location of the inode for the newly created file. The first thing you have to do is look up the directory and check whether a file under the given name is does already exist or not. If it exists, then the creation attempt should fail. Okay. And then it has to scan the directory and directory block and find the empty spots. Okay, this is, let's say this is directory block. Then first, for example, first entry is let's say A.C, second entry is B.C, and third entry is empty, fourth entry is D.C, for example. Then in the course of creating a directory entry, you first have to scan the entire directory block and find the first empty spots, and then create the blocks at this position. What you may want to notice is scanning the directory block is very time consuming. It's very expensive operation. Okay, so if you write an application, that frequently create a file, then your file system should be very, very efficient in creating a file. And every time when you create a file, you cannot linearly scan all the directory blocks to find empty spots. It is going to be very, very expensive. Anyway, you might want to have use more sophisticated data structure for creating a file, especially in finding empty spots in the directory block. Okay, so this is how we create the directory entry. Let me skip to the next slide. Now the directory lookup. Directory lookup is it takes directory pointer, and it takes the name, and it takes directory entry pointer and offset. So the lookup is a function, and it checks if the file name exists in the directory or not, and then it returns the address of directory entry structure using the parameter it has applied. Okay, so there, this is input for a given directory. Find the name, and then return the address of directory entry using the parameters applied. This is lookup. The next function we're going to cover is opening a file. So it is it's called filesystem4-background, and it gets the name. So it's opening a file system, and it returns to the pointers to the struct file. So filesys_open is a system called filesys_open is called by system called open, and it does two things. First, it adds inode to the open inode list. It adds an inode to open inode list. Second, it allocate an initialized struct file and return its address. Okay, so the first one, you have to first check if the file has already been opened by the other open system core. In that case, you do not have to insert the same inode to the list twice. Instead, you just increase the reference count of the inode entry in the inode list. However, you have to allocate and initialize struct file structure every time when a file is opened, meaning that every time the file sysopen is called. So this is the process of allocating and opening a file. This is a process of opening a file. The name of the file, let's provide an example. The name of the file is test file. A file sysopen test file consists of the following 5 steps. First, you have to read the inode of the root directory first. And then you scan the entries in the root directory and find the name test file. Okay, you scan the directory entries and then you find test file. And then you find the matching inode, and we find it that the inode number for test file is 7. So as a third step, you have to insert in-memory inode test file to the inode list. So you are done with inserting an inode to the inode list. And then as a next structure, you allocate a struct file data structure. Every time you open a file, you have to allocate a file struct data structure, and you set the address of in-memory inode and return its address. Of course, it is possible that the inode for test file is already exist in in-memory inodes. In that case, you don't have to read it again or insert it again. This is system core for allocating or opening a file. Okay, so most important step of allocating most important task of opening a file is allocate and initialize struct file and return its address. Okay. So you return the file open for the inode. So find the inode number for a given file and call file _open. So this is essential function, and it allocates and initializes struct file on memory. So next function is directory lookup. Directory lookup is an easy function. It opens a directory and looks up the file under the name and return the inode. So that's what directory lookup is for. Once you find the associated inode, it's time to open a file. So you get the inode, you supply the inode number to the function file _open. The role of file _open is allocate the data structure for struct file and then initialize it and then return its address. So allocate file struct, or let's say struct file, and initialize it. You fill it with some value and return the pointer, return the start address of the file. And what is the process of initializing the file structure? Initializing the file system file structure is right here. Okay, the file structure has a pointer to its inode. Okay, and then the most important attribute to file struct is the offset. Here we call it as a position. The position stands for the offset for a file where we apply the read and write operation. So this is called offset, and in Pintos it is called position. And when you blindly open a file, you have to set the deny write field as false. Okay, but if this file is executable, or for some reason you may want, for some special case, you may want to write this field as true. Okay, so this is the important step of initializing the file struct file when opening a file. So creating the inode and initializing the position. So that's what the open a file is for. Let me provide the steps of removing a file. The matching system core is filesys_remove, and it is called by system core remove. What it does is to set the flag removed on the inode to be true, and then remove the directory entry. That's the two steps it needs to do. So set the flag and remove the directory entry. So this is the flow. It opens the root inode and searches the root directory for a given file, and if it does not exist, then it deallocates the root directory inode, then return false. Means basically the deletion fails. If the directory, the file exists in the directory, then the directory entry becomes false. The in-use field of the directory entry will set to false. And inode of a file removed will be set to be true. And then it deallocates the in-memory inode of the root directory and return true. This is the example of removing the test file. So we call filesys_remove, we call test file. Okay. Then it reads the inode of the root directory, and then it scans the entries of the root directory and finds the associated file and the set in use as false. And for the inode, it sets the removed field to be true. And let's look at the actual code. So it does two things. First, it removed the target file entry from the directory, and then it set the removed flag from the inode to be true. So that's basically two things it has to do. First, it removes the directory entry to be true and sets the flag. Okay, so let me examine the function directory remove. It removes the entry of the target directory, and then it sets the removed flag in the in-memory inode to be true, and then write the updated directory entry on the disk. So this is the details of the directory remove. It gets two functions. First one is target directory, and second is name. This is the name of the file it wants to be removed. So first step is search the directory and get the associated directory entry and make it as false. And then write back the updated directory back to the disk. So inode write add, and then update the disk contents of the associated directory. And after removing the directory entry, it's time to remove the inode itself of the file. The first thing you have to do is it opens the inode, and then it calls a function called inode remove. But calling inode remove does not mean that inode is immediately deleted, because the inode might have been opened by the other process, more than one process. So in inode open, add in-memory inode to the open inodes list, and then called inode remove. In inode remove, the most important part is sets the removed flag in the in-memory inode to be true. Okay, that's it. So it does not do anything other than setting the removed flag to the inode to be true. Nothing more than that. And then after that, we call the function inode_close. In the course of calling the inode_close, it does all the dirty works. So it checks the reference count, and it checks if there are any other process that refers to this inode. So if all is completely free, then it deallocates the associated inode from the disk and then make the associated sectors free. That's the role of inode close. So this is and of removing a file. So in this chapter, we have covered a few details of the file system interfaces. Formatting a file system, creating a file, creating a directory and look up a directory, opening a file and removing a file. This is the basic steps of dealing with the files in the Pintos file system. So we're done. So happy OS.